Hello and welcome to another INB382 video. This time we're going to concentrate on Guro and Phong shading and lighting effects in Unity via the shaders. So as we can see here, I've just got a very simple scene with a couple of spheres. Spheres are very Jim dandy for doing lighting because they show the effects nice and clearly. With a simple camera model, blah blah, and then as we can see here in the game, I'm not even going to execute this because I can play around with this just by using the IDE. So as you can see, I've set up the environment to show two aspects. First of all, what you'll see here is that we have differences in the appearance of the shading of the objects. On the left we have Guro shading, not Gurod, Guro, and on the right we have Phong shading. And you'll notice the difference in the quality. On the left-hand side, the Guro shading, because it is interpolating colours, not normals, you get this sort of blotchy appearance across the vertices. But it's cheaper because it's on a per vertex basis. On the right-hand side, we have Phong shading. We see we've got this nice, smooth looking highlight. The shading is much smoother, and we don't get that blockiness that we see on the left-hand side here. So, but that is done on a per pixel basis, and that means it's much more costly. However, this is not such an issue for modern GPU systems. But to keep aware, just keep aware that when you're designing your algorithms, you may need to make decisions about whether you do something in a vertex shader or whether you do something in a pixel shader. Some issues that come up here are just the cost of pixel shader compared to the vertex shader versus the quality of the appearance. For instance, if I move that Guro shaded sphere way back, I probably won't be able to tell the difference. So when you're doing level of detail work with scene graphs, you can sort of modify your shaders to work in vertex shaders with lighting at a distance with no loss of perceptual detail. One of the more sort of tricks you can do when you're rendering things with a scene graph. But I digress. So these spheres here are just an introductory demo that shows how basic shading and basic lighting up to sort of ambient, diffuse and specular models work. So moving right in, I'm just going to highlight one of the spheres. This is the Phong sphere on the right, and you'll see that the shader has a number of exposed elements from the top of the shader. So if I go to the code, you'll see for Phong, in the properties, these things are exposed in the IDE, as I've been saying, back to Unity. So I can play around with these values on the Phong shaded sphere on the right. So for instance, I might want to change its material properties so that the colours change. So this is the diffuse property, and you'll see that if I move it up and add some more red, we get a purple looking sphere. But it covers the diffuse component of the shading. So I can take that back because that looks icky. And we can do that as well for the ambient component. So I can bring that up as well. There's not much ambient reflection occurring in this value because, as you can see down here, the ambient light value is fairly low. So understand the mixing that occurs here. So you don't see much ambient light components here. If I turn up its values just on the red channel, and all of a sudden the ambient lighting goes way up. So you can see that it just gets this overall red color for that simplified ambient component that we have in this model. So I'll go back to here, bring that back. Not so much into magenta. So look, as you can see here, look at your theory notes in the lecture and understand that all of those parameters, they form the part of the basis of the lighting values. So again, I can play with the specular component here, and what I'll do is I'll remove the red down, and you'll see, actually I might even bring down the green as well. All of a sudden the specular on the right hand side, Phong shaded sphere, turns blue. So this is the specular light component So remember, when you look in the theory notes, you'll see that there's two components. There's the material properties of the object, so how it reflects the light, and then there's the light values themselves for each of the components: diffuse, ambient, specular. And so that's what the light source is. In this case, it's a big, bright white light, low ambience, just to show some nice shading there so the background doesn't bleed. A bit of diffuse and a strong specular component, all white. Play around with those values and you can change the appearance of the object in Phong and Gouraud shading. That's all just straightforward sort of shade theory. The other components to the model include a light direction. So at the moment we've got the light at y equals 10, z equals minus 10, x equals 0. Okay, so if I want to, I can lower the light by changing the y value. So if I set it to 0, the light is straight ahead. From this camera position, you end up with a specular highlight there. So if I move it up again, moving it up in y, and then back up to its original position, then you can see I can change the position of the camera, the light direction. I won't touch the camera position, but the other one I want to play with is the specular power. So here we see that this is how big that white dot will be. This is the reflectiveness of the surface. So if this is a perfect specular reflector, it's a mirror. So whenever you look at the mirror in the morning while you're preparing to come to university, you are looking straight at a perfect specular reflector. So in the end, this simple model here, which does not mimic a mirror, we can change this parameter, this exponential power and the function that you see in the lecture notes, and it changes the nature of that specular dot on the sphere, which is why we use spheres, because it shows it up nice and clearly. So, all right, so if I make that value, so at the moment it's at 10, if I make that smaller, so say to 5, all of a sudden the specular part bleeds out and becomes bigger. If I make that 0, we just end up that the specular value is even across the surface of the sphere from this eye position, and therefore we have this really blobby looking specular. So as we raise the powers, there's a fall off that occurs. And as we raise it up and further, it falls off more quickly until we get, if we want something really shiny, we can make it 100, and then we end up with this tiny little dot. And it starts looking like a billiard ball. Billiard balls are very shiny because they have very smooth surfaces. So these are just the components here. Take it back to the default, which was 10. So all those parameters have come from the properties section of the shader. And you can see they're exposed and you can play with them, but you can also set them in scripts. So if we move back to our programming environment, here's our simple lighting C# script, and we'll see again the commands render material set vector for the components of the lighting model. Again, these are all variables inside the shader, and we're setting them to the various values to make our default blue looking environment. You can see there, first of all, there's material properties, how the object reflects things. The second group is the light components, and the third group is the camera model, the light direction, the camera position or the eye position, and the specular power across the surface. So, how does that create this? So these are the general principles. Gouraud on the left, Phong on the right. All the variables from the parameters are exposed. You can play with them just to understand how they work. But then we go back into the shaders and we see that the shaders operate in a different manner. So let's go to the Gouraud shader. So again, here's the property section, which enables us to modify internal state. So there they are declared at the top. They're replicated down here inside the CG shader proper. So remember, this is Shader Lab up the top. Down here is CG. This is the place where things are modified properly within the CG program. Keep on going down and we get to our vertex shader. Now if we have a look here, the vertex shader for Gouraud shading to implement Phong lighting in a Guru shader, we see down here that it's quite largish respect to the pixel shader. Why? Because it's doing the lighting on a vertex by vertex basis. So that's cheaper, but of less high quality. And you'll see all the components are here. So this is where we calculate our to I direction. We transform the vertices into a world position. We also do a final output position for the pixel shader, which is we project the input position via the MVP matrix, that thing that you're going to see many times in your shaders. We inverse transpose the normal, which I'll get to in the lecture, and a few other bits and bobs that make up the specular, diffuse, and ambient components of the lighting equations. They are then added together to form the final color of that vertex. Add them together here. And we just copy out the alpha channel. It's all good. And then when we get down to, so what happens is, all right, this is where the lighting occurs in the Guru shader. The output goes out, and then we come back into the pixel shader. And the pixel shader is just a pass-through. Nothing happens. There's no calculations done at the pixel level. They've all been done at the vertex level. And the colors are then interpolated across the triangle as it's rasterized. So this gives us the final appearance, which is a bit blocky and a bit inexact, and has all sorts of problems that I cover in the lecture. Moving right along, we go to the Phong shader. Again, Phong shader, it's got the properties at the top with the exposing. We expose all the elements of the lighting model and material properties. All good. Cover that same as the Guru shader, but have a look. The vertex shader is much simpler. It's basically, it's not a pass-through, but what it does is it just transforms the input positions by the projection and to the model view projection matrix so that we have projected positions coming out. It generates a position for the points in the world, so it does an object to world transform. Calculates the correct transforms for the normals. But then when we get down to the pixel shader, this is where all the action happens. So for Phong shading, the vertex shader sets up some elements that are needed, some transforms, but no lighting is calculated. All the lighting is calculated here. And we see it replicates the Guru shader calculations, but it does them within the pixel shader. And this enables us to have this nice smooth shading because we're actually interpolating the normals. Okay, so in the Guru shader, we calculate for each vertex and each normal at each vertex. Here, we are actually interpolating the normal. A new normal is generated for each pixel, and then we do our calculations. And this makes our lighting much more precise, thus producing a much more visibly impressive appearance, which we see when we go back to the Unity shader over here. So that's the basics of the use of Guru and Phong shading and the shaders, the variables that you can modify, and the source code that you can see and play with. Thank you very much.